Hi, this is going to be the second session on functions from R to C. In the first session, we define continuity and differentiability of functions from an interval to R, of course, continuous function in differentiability. Then next we define integration of such functions under the assumption f is continuous, right? There are two facts which we need because these facts will be repeatedly used for the course, so we will establish them today. And if you have watched many of my analysis videos, you would have understood whenever you deal with the integral, it's not important to get a close to form of the integral. It's very important to learn how to estimate. Okay, that's very important. Even if you get close form, something like e power x times cos squared x, what is it of use? Okay, you want to use in a real life, you have to estimate. You have to find some good approximation to work with it. Yeah, so you learn to do that. That's always analysis. Okay, so let us go start with this. So we define let f from an interval a b to c be continuous, and we define, if we write f equal to u plus iv, then we define interval of a to b f of t dt. Usually I will even write simply a to b f. Okay, is interval a to b of u of t dt plus I times interval a to b v of t dt. Okay, and what we found is, if I look at all continuous functions on the interval a b taking values in c and look at this map, and f going into interval a to b f of t dt. Okay, this is a complex vector space over C, and this map is a complex linear map. Okay, this more or less I asked you to check. I hope you have done that because it's a trivial exercise. Okay, and you are all, I expect most of your master's degree student gone through analysis courses, so it should be easy, right? Okay, the first thing we want to do is the integral inequality. So what does it say? Suppose f from a to b to c is continuous, then I know a to b f of t dt is a complex number, right? Then I want to estimate this in modulus. Remember, in the case of f from ab to r, you had already done that. You must have learned interval a to b f of t dt in modulus is less than or equal to interval mod f of t dt from a to b. This is okay. This is known from your real analysis course. We want to do similar thing for complex thing. Okay, let's go through the proof. Suppose this is 0, a to b f of t dt is 0, then whatever estimate you want to do, this will be some positive non-negative real number, it will be true. Okay, what we want to say is this mod f of t dt. Okay, so this is non-negative. Remember, t going to modulus f of t is continuous non-negative function, therefore the integral will be non-negative, right? And if this is 0, then 0 is less than or equal to some non-negative number is true, right? So we assume that this is not equal to 0. Okay, then okay, yeah, I know that f of this dt, I can write it as modulus of this fellow f of t dt, this complex number, into some e power I theta. This is a complex number, therefore I can write it as r e power I theta, where r equal to this, right? Therefore r, which is modulus of f of t dt, remember the modulus is outside, is nothing else than e power minus I theta times integral a to b f of t dt. Right? Multiply this. Is that clear? Yeah. Now this is gold mine. Do you see why? Remember, e power I theta is a complex number and a to b f of t dt, okay, f going to this is a complex linear map. So what do you think I can do? I can push e power minus I theta inside. Therefore this fellow is nothing other than a to b e power minus I theta f of t dt. This is because C linearity, this is complex linearity of the integral. Right? Okay. Now notice that this is supposed to be a complex number, but is actually equal to r. Therefore what is this? This is the real part of this complex number. Do you understand this? Yeah, this is some complex number, call it something like alpha or whatever, okay, but that alpha happens to be r, that, okay, therefore real part of that is equal to r. You understand that? Therefore this is equal to real part of a to b e power minus I theta f of t dt. Right? Okay. Now this is a real part of this number, right? But remember, okay, how did we get the real part of this integral? Recall, yeah, recall integral of f by definition is integral of real f plus I times integral of imaginary f, okay, where real f is u, imaginary f is v, etc. Keep this as a mnemonic, okay. Therefore this fellow is nothing other than a to b real part of this integral e power integrand e power I theta f of t dt. Do you follow this? Yeah. Now how many of you can see something very interesting has happened now? I'll keep this in front of us, right? Now this integral is something very interesting. It is integral of a real valued function, okay. This is real valued. You understand this? Right? Therefore what I know is, since f is less than or equal to mod f, okay, integral of a to b f is less than or equal to integral mod f. This is for true for anything. This is f real, okay. This is recall, okay, right? So I am going to use this. This is a digression, okay. We are going to use that, okay. So what are we going to do now? Therefore this fellow is less than or equal to this guy, okay, is less than or equal to a to b modulus of real part of e power minus I theta f of t dt. There is a modulus here, right? Now again, next recall, second recall. If z is a complex number which x plus iy, then mod x is less than or equal to mod z, right? Therefore this fellow is less than or equal to a to b of modulus of e power minus I theta f of t dt. Now notice that e power I theta, this is modulus of two complex numbers, therefore it's modulus of product of two complex numbers, therefore this is mod e power modulus of e power minus I theta into modulus of f of t. The modulus of e power minus I theta is 1, therefore this is nothing other than modulus f of t dt, right? So now let us go back. I started with r, which is modulus of the integral, and what I have shown, it is less than or equal to integral of the modulus. Is the proof clear? It looks like almost like a magic, right? Okay, just love this proof. Okay, go back. So you please rewind, go back and understand this proof. I don't want to again go back. It's you should do it on your own now. Pause, review with, and then proceed. So let us recall. So what do you have? Absolute value of the integral is less than or equal to integral value of the absolute. Integral of the absolute. Right? Absolute value of the integral of a function is less than or equal to integral of the absolute value of the function. This is a mnemonic. This is over the interval only, a to b. Okay? Keep that in mind. So what is the use? The first serious use, okay, we will give the first application of this thing. This will be very much needed. Suppose fn's are from a to b to c and f, okay, are continuous. Okay, assume that fn converge to f uniformly on AB. Let me just check whether I started sharing. Yeah, good. Okay, then we know f is continuous. Right, therefore integral a to b f of t dt makes sense. So what is that we want to claim? Okay, conclusion, integral a to b fn of t dt, this is a sequence of complex numbers. These complex numbers converge to the complex number f of t dt. Yeah, is that clear? This is the most important result. It's a very trivial proof. You might have seen this proof in real analysis. It's exactly the same thing. So to prove this sequence of complex numbers converge to this, what is that I have to do? I have to estimate their difference. So I have to estimate, okay, modulus integral a to b f of n dt minus integral a to b f of t dt. Right? But remember, by the linearity of the integral, this is same as integral a to b fn of t minus f of t dt and modulus. Yeah, but by the last integral inequality, this is less than or equal to absolute value of this integral is less than or equal to absolute value of this integral fn of t f of t dt. Now you should know how to prove it on your own, right? Since fn converges to f uniformly on AB, okay, if you give an epsilon positive, I know there exists a capital N, a natural number. So that what happens? Whenever n is greater than or equal to n, and for all t in the interval AB, I have modulus fn t minus f of t is less than epsilon, right? So if I choose any n greater than or equal to capital N, then what happens? Immaterial of which t I chose, this fellow will always less than epsilon, right? Therefore the integrand, let's look at the integrand. Integrand is fn of t minus f of t, this integral, okay, as a function is less than or equal to epsilon. This is a constant function, right? So what do I get? By monotonicity of the real integral, okay, remember this again, recall, if f and g are real valued, continuous, suppose f is less than or equal to g, then integral a to b f is less than or equal to integral a to b g. Yeah, continuous on the interval ab, etc. Okay, so I am going to use that. Therefore this is less than or equal to a to b epsilon Okay, this is epsilon into b minus a. Right? Therefore, I have shown for all n greater than or equal to capital N, okay, the distance between a to b, fn of t dt minus a to b, f of t dt is less than epsilon times b minus a. This is strict because here it's strict. Okay, anyway, it doesn't matter. Okay, so if you want epsilon, what do you think I should have done? I should have done here. If you want strict also, you could have done 2 into b minus a. Therefore, that will be less than or equal to f. Okay, therefore strictly less than epsilon. So I got it. Yeah. So pause, review, proceed. Hi, welcome. This is second part of the second session on functions from R to C. So the last for 40 minutes or so, of course including the first session, we had been discussing about integration of complex valued functions, and we concentrated on the theory. But again, my practice shows it's all nice, but when you give very concrete examples, students have a lot of problem. Okay, so what I'm going to do is to discuss two examples. Okay, and those examples are also good, and in the sense that they also illustrate various points of the theory on the way. These things are usually not done, and you will also be surprised. The first example, we are going to compute a real integral converting into some complex integral. Okay, many of you might have heard about the word one uses a residue calculus, residue theorem to compute real valued integral, but you are going to see even before that I could compute a real integral. Again, I will give another example when we come to Cauchy's theorem also. Before anything to do with the singularity, residue theorem, nothing. Okay, I hope you will enjoy. Please go through it. Okay, since it's a computation, I'm usually good at computation when I'm doing on my own pen and paper, and whereas when I'm trying to explain, my concentration is more on that, so I do tend to make some trivial mistakes. Okay, but learn to ignore them, but I'm confident you can do on your own. Okay, much more correctly and precisely. Yeah, okay, let's get started. Yeah, so essentially these are two exercises, exercise 616 and 6112, but I'm going to do them as examples. Okay, right. The first example is to compute a real integral. Okay, this is the first example. Example 1 is to compute a real integral of the form 0 to t e power ax and cos bx, where a, b are real numbers. Let us assume the ordered pair a, b is not equal to 0 vector. This is what you want to compute, right? Notice that this is a real valued integral, right? Real integral. So I want to compute. So how do I do that? Okay. The trick is we want to convert into finding integral of a complex valued function. Now how will I get it? Remember e power ax and cos bx, and you should remember something, e power it is cos t plus I sin t. Therefore, if I have e power a plus ib, okay, into t, what will be? It will be e power a t, right, times e power ibt, but that's going to be e power a t into cos bt, sorry, e power a t cos bt plus I sine bt. Now do you see the trick? Right? So what is that you are going to assume? We are going to replace this by an integral of this form 0 to t e power lambda x dx, whereas lambda is a plus ib. Right? You got e power ax, the real part is going to be into cos bx. Right? Do you like it? Yeah. Good. Now remember, if a is 0 or b is 0, this is very trivial. If a is 0, this is cos bx. If b is 0, this is e power ax. These are all computed very easily by 12 standard thing. So let us assume ab is not equal to 0. That's what I did. Okay. Right. Now therefore what is that I have to compute? I have to compute this integral, and remember this is a complex valued function. Right. Therefore what is its thing? This is equal to 0 to t of real part of this dx plus I times 0 to t imaginary part of this dx. Right? Therefore real part of this integral 0 to t e power lambda x is real part of this object. Okay, 0 to t real part of e power lambda x dx. But as we saw, this fellow is nothing other than, what is e power lambda x? Let me just quickly again go through. This is going to be e power ax into e power I bx, but that is going to be e power ax into cos bx plus I sine bx. Therefore the real part is going to be e power ax cos bx. This is the real part. The imaginary part is e power ax I times e power x and sine bx. Right? Do you follow that? Good. So it only shows that therefore I have to compute what this is. Right? So let us, therefore the idea is to compute 0 to t e power lambda x dx. Right? But that's very easy. Yeah? What is that? We know that dy dx of e power lambda x by lambda. Remember, now lambda is non-zero. Right? Therefore lambda is a complex number which is non-zero. Therefore this makes sense. This is e power lambda x. Therefore this fellow is nothing other than e power lambda x by lambda evaluated between 0 and t. Yeah? Have you understood this? So make sure you see that this is a beautiful thing. Right. Now how do I compute this? Okay. Again let us go back. Now remember, e power lambda x, let us write it. E power lambda x by x, we will write as complex number. This is going to be e power a plus I b times x by lambda, but that's going to be e power a cos bx by lambda plus I time, right, e power ax, sorry, it's not e power, it is e power ax, yeah, cos bx. Should I write it separately? Yeah, I think it will be better so that I myself don't get confused. Sine bx. Therefore this is going to be e power ax cos bx by lambda plus e power ax, I is there, sine bx by lambda. So now notice that this is where you must be alert. Okay, if you think this is the real part, that's wrong, because lambda is a complex number, right? Therefore I should know what is 1 by lambda. Similarly here 1 by lambda. Now let us look at. So you can see this is simply complex arithmetic, right? If you remember, I said I hope all of you know how to work with algebra of complex numbers, basic metric properties, etc. So I did not spend time on that, right? Now in this example I have to do such things. Okay, let us do that. So what is lambda? See, 1 by lambda. So I hope all of you know how to do that. This is lambda bar by lambda into lambda bar but that is lambda bar is a minus ib by a squared plus b squared. Do you understand that? Yeah, right. Therefore, okay, I don't know why I'm not going to go to the next page. Yeah, so I may need this, so let me do that. Therefore, so let us look at the, so e power ax cos bx by 1 by lambda, that is a minus ib by a squared plus b squared, right? The next one will be a, are you following? A into a squared plus b squared into e power ax, there is an I sin bx, but there is also another thing. This is, there is a I here, this I, okay, 1 by lambda. 1 by lambda is what I am going to do. Maybe I will do 1 by 1 so that everything will be clear. Okay, so I have e power ax cos bx a minus ib by a squared plus b squared. Okay, therefore what is the real part of this? Remember, a is positive, x is positive, sorry, a and x are real, therefore e power x is real, cos bx is real, a by a squared plus b squared is real, but after that I multiply with minus I, that will be common. Therefore this is nothing other than e power ax cos bx, there is a time a by a squared plus b squared. Yeah, right. The next one is the same thing. I have 1 by lambda, that is a minus ib by a squared plus b squared times I into e power ax sin bx. Yeah, by 1 by lambda is what I would have done. Okay, right. Now notice that this will be a by a squared by b squared into I times e power ax, etc. Therefore the real part of this is going to be minus ib by a squared plus b squared I e power ax sin bx. Okay, therefore minus I into I will be plus 1, therefore b by a squared plus b squared and e power ax sin bx. Okay, real part equal to this, right? So what is that I have found? Therefore I have found the real part of e power lambda x by lambda is nothing other than a by a squared plus b squared e power ax cos bx plus b by a squared plus b squared e power ax sin bx. Therefore I can write it as 1 by a squared plus b squared, and there is still one more thing which I had forgotten. I will come to that, into e power ax also can come out, therefore a cos x, a cos bx and b sin bx. Yeah, right. But notice that this one, this is, that is at, this is e power lambda at, therefore at t this is going to be e power a t by a squared plus b squared a cos bt plus sin bt. Okay, remember what I am doing is I found out the interval to be e power lambda x by lambda. This I am supposed to evaluate at 0 and t. So at t I have found it, at 0 I have found out. At 0 what is this? At 0 e power lambda x by x at x equal to 0, lambda at x equal to 0, this is going to be 1 by lambda, therefore it's going to be minus, okay, a minus ib by a squared plus b squared. Therefore, real part of this fellow is going to be, remember there is again an I, okay, minus b by a squared plus b squared. Yeah? Do you accept it? Okay. But remember, therefore, real part of e power lambda x by lambda between 0 and t is going to be, I hope I will write it carefully, a cos bx plus sine b, maybe a t, so b sine bt by a squared plus b squared minus b by a squared plus b squared. I hope I did everything correctly. Okay. What do I want? At 0 it must be minus b. Okay, let me just make sure the answer is correct. Yeah, but I should get a minus a in my thing, so I do not know where I goofed. 1 by lambda, this is ib, right? E power lambda x by lambda. Oh, I want the real part. I'm sorry. Yeah, the real part. Real part of this, you can see I did a mistake. It's not imaginary part. Real part is here. You see that? This is here. Okay. Please correct this. Okay. Plus a. This is what I said. Okay. Right. So we found out the answer. Okay. Therefore, what I found? 0 to t e power ax cos bx dx equal to 1 by a squared plus b squared times e power ax, okay, e power ax a cos bt plus b sin bt, okay, and the whole thing is again e power x minus a. This one I should erase. Okay, I hope I did correctly. This is a plus a. Again I did a mistake. You can see that. Okay, go through this and so my suggestion would be just watch it once on your own, then stop the video, pause the video, do it on your own. Okay, as I did some trivial mistakes, you may also do it. Sometimes you may forget. Okay, there is a lambda, 1 by lambda, imaginary part, all those things. It's all likely to happen because, to be very frank, when I did this exercise maybe a few decades ago, I got it correctly because I was almost a student at the time. Okay, now when I thought of this today, okay, I was little making stupid mistakes because now, okay, I'm more theory oriented than computation. Okay, that's the reason. But you are all young. Okay, go through it. Okay, I hope you enjoyed this. Okay, now let's go to the second. Now the second thing deals with this. Suppose this is example 2. So let us assume I have a power series which is Cn z power n. I can actually make it z minus a power n, and the disk of convergence is bar, but for simplicity let me assume, okay, where r is positive. Right? So this is 0 to infinity, and this so this power series converges in this disk of radius r. Therefore it defines a function f and you know that it is continuous and differentiable, etc. That you will learn in my third lecture on power series. But that's not important. But what we know is the following: if I denote by Sn of z equal to summation ck z power kk equal to 0 to n, then this is all polynomial. This polynomial converges uniformly to f on any b0r, okay, 0 less than or less than r. Okay, this means uniformly. This is my standard notation, right? Yeah. Okay. Now I want to integrate. Now remember, so far what is the kind of thing I have done? I learned how to integrate complex valued function of a real variable. But this one is z going to f of z or Sn of z is complex valued function of a complex variable, right? And also I need the what you call the integration domain should be an interval in R. Those things are missing. So how am I going to produce? This is way I am going to produce. So let us look at C to be the circle of radius R centered at 0. That is, so I can write it as n is equal to R e power I t 0 less than or equal to t less than or equal to 2 pi. Right? Therefore, now I have a function. What is the function? So fix an R 0 less than or less than R. Now notice that my Sn converges to F uniformly on C, because this C is contained in B0 rho, where 0 less than or less than rho less than capital R. Right? Since it converges uniformly on this, it converges uniformly on its subset, and the circle is a subset. Yeah, so this converges uniformly. Is that all right? Okay, now let's go back to the next one. Okay, so now I want to think of this as a function. So what is the natural way to think of this? Okay, take a t. Since R is fixed, then I can think of as f of R e power I t. Okay, where z is R e power I t, this is on the circle. Right? Therefore, this is a continuous function. Okay, on the interval and complex valued function. Right? Are you following? And for a similar reason, look at f bar, that is a complex conjugate, that is f bar of z is, look at f of z and take its bar. Okay, this is nothing other than Cn bar Zn z power n bar or z bar power n. This is the same. Okay, by uniform continuity, uniform convergence, you know that, because what is Sn of z? Sn of z is ck z power k 0 to n. Therefore, this is a finite number of complex numbers. Therefore, the complex conjugate is going to be complex conjugate of each of the term. But each of the term is a product of two complex number. Therefore, their complex conjugate is product of the complex conjugate, etc. Therefore, I have ck bar z bar power k equal to 0 to n. Right? Now, what is that? Again notice that Sn converges uniformly to f and Sn bar converges uniformly to f bar on C. On C is a circle, okay, not complex plane. Okay, are you convinced? Make sure you understand all these things. We are going to make use of them. Right? Okay. Now I want to know what is Sn. So now notice that the next thing what I want you to notice is that this converges on C. What do I know about C? C is a closed and bounded subset. subset of complex numbers, therefore it's compact. Therefore these functions, and also since Sn converges to f and Sn bar of course converges to f bar, it follows that Sn and Sn bar are bounded on C. Okay, since C depends on R, let me say bounded by a constant M. Therefore, are you following that? Sure? Okay. Sn, F bar, these are all bounded by a single constant M R. Please make sure you understand this. Okay. Any convergent sequence is bounded. Therefore, since Sn converges to F uniformly, F is bounded, it follows that Sns are also bounded. The next thing is very crucial. Okay, this is what I said. You are going to really learn a lot of good things about analysis. Okay. This kind of thing will never be ever asked in your complex analysis course, so this may not help you to get good grades. Okay, this because it may not appear as a question or a problem or a seminar topic. But if you learn those things, you will see that your understanding and mastery over complex analysis is extremely good. Okay, so bear with me. Don't think always in terms of what is in it for me. Does it help me to get good grades? Eventually, it will help you to get good grade, and it will also help you to pass a lot of competitive exams and oral interviews. That is the final aim, not simply semester exam and grade. Okay, come back. Now, the next thing is, suppose Fn from x to, let us say C. Okay, this is just a set, and F and Gn and G, these are all function sequence, and assume Fn converges to F uniformly, Gn converges to G uniformly on X. Can I conclude Fn Gn converges uniformly to Fg on X? Not in general, but not in general. Yeah, but what do I know? If one of them is bounded, if let's say mod Gn is less than equal to M for all n, then yes, that is F and Gn converge to Fg uniformly. You see that you have to learn analysis well. Okay, so now let us, as I said, Sn's Fn's are all bounded. Therefore, Sn times Sn bar converges uniformly to F times F bar on C. On C equal to Cr. Do you accept it? Yeah? Okay. But what is this? This is mod Sn squared. And this converges uniformly to mod F squared. Right? So all this is basic analysis. So far no complex thing came. Complex thing of course came earlier. How I reduce a complex valued function of a complex variable by restricting to a circle. I thought of it as a complex valued function on an interval. Learn these tricks. Okay. Enjoy. Okay. Now therefore what do I know? If I integrate 0 to 2 pi, our earlier theorem says mod Sn squared converges to mod F squared 0 to 2 pi. Alright, by the result. Remember, if F are continuous from interval a b to c, continuous, and if F1 converges to F uniformly on a b, then interval F1 from a to b converges to interval a to b of. This is what we proved in the first part of this lecture. Alright, so my question is, how do I compute mod Sn squared? Okay, but therefore this is nothing other than 0 to 2 pi summation Cj, okay, r power j e power I jt, j running from 0 to n, and this is my Sn, and Sn bar is going to be, now write k equal to 0 to n ck r power k e power I kt and its bar, therefore it's going to be minus. Yeah, this is ck bar, but complex conjugate of e power ijt is e power minus ijt into dt. Are you convinced? Okay, now remember integral, okay, integration process is linear, therefore the summation and it's a linear over c, therefore the coefficients come out, right? The constants come out, sorry, not coefficients, constants come out, therefore here they are the coefficients there. That's going to be therefore j and k running from 0 to n of cj ck bar r power j into r power k into e power ijt into e power minus ikt dt 0 to 2 point. But what is this? This object is nothing other than 0 to 2 pi e power I j minus k in t dt. Okay, this we had already computed, right? That is the end of the first session, if I remember right. I computed, okay, e power I n t integral 0 to 2 pi is 2 pi if n is 0, otherwise it is 0, because e power I n t has a primitive, that is the derivative of e power I n t by I n is not equal to 0, and evaluate between the limits of integration 0 to 2 pi, but e power I n t is periodic with 2 pi, therefore the values at the end points 2 pi and 0 are the same, and then the interval is 0. Therefore this is equal to 2 pi if j equal to k, otherwise 0, j is not equal to k. Therefore what do you think I got? Therefore this fellow is nothing other than ck bar and r power 2k, that's it, k running from 0 to n. But what is this? This is nothing other than mod ck squared r to the power 2k, k equal to 0 to n. Yeah, so but what is our thing? Mod Sn squared converges to 0 to 2 pi mod f squared. Therefore mod f 0 to 2 pi mod f squared is going to be the sum of this, that is going to be 0 to infinity mod Cn squared and r to the power 2n. Yeah, if you learn Fourier series, you know what this is. This is the Parseval identity. Okay, pause, review, proceed. So let us summarize. I have a power series function f of z, which is Cn z power n 0 to infinity, and the disk of convergence is 0 or r positive. Whenever you write that, assume that r is positive. I do not keep repeating. Then for any 0 less than or less than capital R, what did I have? I have found, okay, 0 to 2 pi of mod f of, let me write it, r e power it whole square dt. This is equal to, I think there is a 2 pi, I should not forget it. Yeah, yeah, this is, there is a 2 pi, therefore 2 pi, I forgot this 2 pi, therefore this is 2 pi times summation mod Cn squared r to the power 2n 0 to infinity. This is what you have proved. Okay, right. Now let us, okay, specialize this. Suppose my r is infinity. What does it mean? That means Cn z power n converges for all z in complex numbers. Right? Let's further assume my function f is bounded on C. That means for all z in C, modulus fz is less than or equal to m. Right? Now, what do I know about 0 2 pi mod f of r e power I t whole square dt? For every r, this is going to be less than or equal to 2 pi m squared. Just make sure I am writing correctly. Yeah, it is independent of r. Alright. Therefore, are you following? But what do I know? I know that mod cn squared, this is 2 pi, and r to the power 2n is less than or equal to modulus f of r e power I t whole squared 0 to 2 pi dt, but that is less than or equal to 2 pi into m squared. Yeah. So what does it mean? Therefore, mod cn squared r to the power 2n is less than or equal to m squared for all r positive. Yes. Do you see something very interesting? Suppose my c1 is not equal to 0, right? Therefore, mod cn squared r to the power 2n is greater than or equal to mod c1 times r squared, right? That means r squared is less than or equal to m squared by c1 mod c1 squared. But this is true for all r. As r tends to infinity, okay, this goes to infinity, whereas this is bounded. And similarly for all cn, the same thing. And what did I use here? Again, let us recall, because many of you may not have gone through my analysis course. Recall, if I have ans are non-negative, right? And if this is convergent, the sum is nothing other than LUB or supremum of Sn. You understand? Therefore, in particular, my S is greater than or equal to An. That's what I used. This fellow is greater than or equal to any nth term. Therefore, mod Cn squared r to the power 2n is less than or equal to m squared. Okay, this is true for all r positive. Okay, this contradiction shows when n is not equal to 1, not equal to 0, then I have a problem. Yeah? Therefore, what is the conclusion? The conclusion is if f of z is cn z power n 0 to infinity is convergent on C and bounded on C, then it is a constant, namely C0, which is f of course f of 0. This is your Liouville's theorem, as you learn. After doing a lot of Cauchy's theory, you will do that, but you got it. Yeah? Okay. But this should be again compared and contrasted. See, these are the kind of thing, if you enjoy mathematics, you will learn. This should be compared and contrasted. If you enjoy mathematics, you will understand. You see that power series like a polynomial of infinite degree, right? Of course, people will repulse when you hear, when we say such things, but intuitively. Now, what do I know about polynomial? If I have a non-constant polynomial, we will prove it sometime in the course, but you might have learned already in complex analysis. In my real analysis, I proved it. Okay. If p of z is a non-constant polynomial, okay, then mod p of z goes to infinity as z goes to infinity. Right? But power series is infinite degree polynomial, so I may tend to believe the power series in modulus should go to infinity, but that's not what we are saying. Please don't get confused. I'll come back to this when we do Liouville's theorem, because many beginning students have some slight confused idea about Liouville's theorem. What it says is, if I have a function which is entire, okay, which is also bounded, then it's a constant. It does not say an entire function goes to infinity as it goes to infinity. It does not say that. If you have not learned complex analysis, the last 3 minutes you ignore. Okay, we will come back to it when we do Cauchy's theorem. I hope you all enjoyed. Please go through this example. You can see you learned a lot of analysis. We also made use of all the results which you learned in these lectures. Okay, stay tuned, stay safe. We'll come back.